Good. So let's start then. So remember from last time, we computed the cohomology of the n-sphere. And we used the migratory sequence. But remember that basically we didn't need to know all of the information about the map, the linear maps between the different spaces. For the sphere, basically we have a lot of zeros, and that helps us to have a more straightforward computations without knowing explicitly what is each linear map. But now, so that was a very particular case. It was like a very good thing just to get used to the major sequence. But we will see for this example that we will need to know more information about the maps that are involved on the major sequence. So let's start with, let's see. So we will compute the cohomology of the torus. Right, so let's see. Basically, at the end of yesterday's class, you already decided what will be the splitting of the manifold. Right, so it will be two cylinders, like this, U and V. And the intersection will be two cylinders also, right? Now, the important thing to keep in mind is that this is connected, and this one is not connected. Okay, so prior to this example, all of the other examples, U, V, and U intersection V were connected. So this is the first, no, sorry. When we computed the cohomology for the circle, also the intersection was not connected. This was U, this was V. So U intersection V was not connected in that case. All of the other cases that we have worked out, all of them have that condition that U intersection V is connected. Okay, so here we are. Now, the good thing about this splitting is that we know the cohomology of the three pieces that are involved. So U is basically a cylinder, so you have that it is homeomorphic to the cylinder. And also we have computed that a cylinder has the homotopy type of a circle. The same applies for V, so same argument. And also for the intersection, right? So the intersection is going to have the homotopy type of two disjoint circles. One circle here and one circle here. And the good thing about all of this is that we know the cohomology of those three spaces. So we have here the table that gives rise to the major sequence. So tell me how to fill the table.
So for 0 and 1, the homologies of both the circles, well, the circles are gonna be R. So the first two lines, for example, we have
So this is
R,
R
R.
and R here because of the circle, like this.
No, but R union. What is joint union R?
Oh, right. I only wrote down U, right?
Mhm.
And then for V, what else?
And also for the two dimensions, it's gonna be 0,
In degree
0.
2, 0, okay?
And in the zoom missing, you're gonna have also R, R union R.
R plus R, right? Like this, okay? And again, the problem here, or the simplification is, here we don't have an R, so we will need to consider all the exact sequence that starts from here. We cannot simplify this and start here, right? Because U intersection V is not connected. Good, so we will put all of this information here. That's what we have, okay? Uh, Here, the map alpha is this one here. And I also have a map beta, which is this one. Okay, so this 0 starts here and we go all the way up to here. So that's a long exact sequence of vector spaces. Now, this is an unknown vector space, and this is another unknown vector space. So we cannot use the dimension formula, the alternating sum of the dimension equals to 0, to try to figure it out what are those two vector spaces. So we need to do something more. And also notice that once we start here all the way up to the end, we don't have any zeros. I mean, this could be 0 and this one, but other than that, we have non-zero vector spaces. So this long exact sequence I cannot treat it like separate short exact sequence like we had something yesterday for the sphere. Remember the long exact sequence? We had many zeros, so we only had to focus on small sequences. Here is not possible. So that's the difficulty compared with the previous examples. Okay, so what we will do, we will understand this map, right? In degree 0. Remember that this map corresponds to going from degree 0 here to degree 0 there. So we will understand alpha, And a similar argument will lead us to understand the map data. Right, so let's do that now. That's the map alpha, okay? Now, I'm not going to draw U, but basically some important aspects about UV and the intersection. So something like this is U, and then this part here and this part here corresponds to the intersection. Okay, and somewhere there you will have V. Okay, now yesterday, we discussed, we recall what H0 is. U and V are connected. So remind me the elements here, what do they stand for? So you know that this is R because U is connected. This is R because V is connected. You know that this is R2 because U intersection V consists of two connected components. But what are the elements of degree 0 in cohomology? Anyone?
The smooth functions.
Moises, come again?
The smooth functions.
Smooth functions?
Uh,
You have to restrict that set. Omega 0, that's correct. So omega 0 of a manifold X, smooth functions on X. That's true. But I'm talking about cohomology. So H0 of U is R, but what does it mean every number here? If I take the number 3, what does it mean regarding the manifold U?
I think they were functions that were locally constant.
So in general, right. So H0 consists of locally constant functions because U and V are connected. So any real number there stands for a constant function. Okay, that's good. Very good. Now, do you remember? So here, again, we need to go a little bit into the how the major vectorial sequence was defined. So in general, you have alpha. I would put it, let's see, let's do it. It could be either functions or differential forms. X, a differential form on U, V, a differential form on V. Finally, Y, a differential form on V. Then remember that this, the definition was, I have this differential form, X, I have to restrict that to the intersection. And then I do the same for the function or the differential form Y. I restrict that to the intersection and I take the difference. That's in general how that function is defined. You have a differential form on U, a differential form on V, and you restrict it only to the intersection and then subtract. In the case that we are analyzing at this moment, we are only interested on functions. So I have a function on U, constant function, a constant function on V. This is the function. Instead of all of U, I will restrict that function on the intersection. This function is on V. I restrict to the intersection and then subtract. Okay? So that is the definition of alpha in any degree. Now let's focus on degree 0 of functions. So there it is. I take a constant function A on U and then this one on V. I'm writing the same function, but you should think of this function restricted. This is the one cylinder. Remember that U intersection V is two cylinders. This here is what I would like to have here. This is one part and this is the other one. So this is this function, this other function. That's basically the constant function A minus V on this part, and the same function A minus V, but now on this other component. Is this clear? Any questions on that? No? Okay. Now, that's alpha. Remember that this is R, this is R, and okay. So you have a formula for alpha. You know what it is. You take A, B, and it goes A minus B, comma, A minus B. That's basically what we have said. So we know exactly what is alpha, that linear map. Even here, we are on degree 0, but we can do it on any other degree. I can argue in the same way. I have a differential form alpha, beta, a differential form gamma, and I restrict beta minus gamma, comma, beta minus gamma. Right? Because here I have the differential form beta, and here gamma. Okay. So what you should take from this, since you know alpha now, what can you say about the image of alpha? Alpha is a linear map. The image has to be a linear subspace. What can you say about that linear subspace? What is the dimension of the image of alpha? That's the formula that we found for alpha. So now we have a linear map. What is the dimension of the image?
1.
1, right? So now you know the dimension of the image of alpha. Nice. Okay? Good. So far, we understand this map here. We have a formula, we know what is the image, kernel, everything, because we have a formula for that linear map. In a similar case, we can argue for beta. But instead of having a locally constant function or a constant function, I have a one form on U, a one form on V. The definition of this map is the same. The differential form on U is restricted to the small open set U intersection V. And then we have to subtract. Okay? Now, remember that this is R, because U and V are the circle, and U intersection V is the union of two circles. So again, the whole idea is to understand the map beta. But it will be the same. The image will be one-dimensional. So I have a one form on U, a one form on V. I restrict it to the intersection and then subtract. On the other connected component of the intersection, I have the same value. Thus, the dimension of the image is also 1. Okay? So it is the same argument has in degree 0. And that's about it. That's all that we need to know to compute the cohomology. Let's see. So this is the same exact sequence, the non-exact sequence that we had before. The only difference now, just for reference, I put f. We don't know the function f, but we know very well the function beta and the function alpha. We know what those two linear maps is. F, we don't know it, and we don't need to know what is f. So let's try to compute the dimension of this vector space. Once that we compute the dimension of this vector space, then we can argue, as always, with the alternating sum formula to compute the dimension of this. Okay? So let's focus first on this one. Now, we have an exact sequence, and this map goes to 0. What can you say about f? About the linear map f?
That it is rejected.
F is surjective. Great. So that means that H2 is equal to the image of f. Right? But now, by linear algebra, the dimension of f is the domain over the kernel. Okay? We have that. And now, again, we use the fact that we have an exact sequence. So the kernel of f is equal to what?
The image of B.
Right. So this vector space is equal to this one. And I know what is the dimension of beta. In fact, we know that it is basically v comma v, right? It is one dimensional beta. That means that H2 of the torus is one dimensional. Okay? So now we know this. Any questions? Okay, so again, because this is an exact sequence, and I know all of the vector spaces that are involved, except for this one, using the alternating sum of the dimensions result, we know the dimension of this space as well. So what is the dimension of this one? We know that this is one dimensional.
It's two-dimensional.
Correct. It's two-dimensional. Right, now you know this, so you can compute that. And we are done. Now you have computed the cohomology of the torus. Right? Any questions? So this computation compared with the computation of the spheres that we worked out yesterday is more involved because we don't have any zeros in between. And on yesterday's computation for the cohomology of the sphere, we had many zeros. Basically, everything was zero. So that's why yesterday's computation was more straightforward. In this one, you see that it is a little bit more involved. But still, I mean, notice that we don't need to know what are all the linear maps involved there. Basically, we only need to know, for this example, this map. I decided to start with alpha for functions and then argue beta, but for the purpose of computations, you don't need to know the linear map alpha. It suffices to know beta, and that's it. Great. Are there any questions? Okay, so let's move forward. Now, right. So the next example is to compute the cohomology of the surface of genus 2, like the two torus that are combined like this. So we need to do that now. So let's see. Again, there are, compared to yesterday's computations, there are a little bit more involved. In terms of difficulty, it is the same that we have done for the torus. So I'm going to state a result that it will be useful. I'm not going to prove this. So consider the manifold that it is the torus minus a point. And then take n to be this punctured neighborhood here. So basically n is a disk minus the point that we are omitting. So n lies inside of the puncture torus, and I call that map J. It's the inclusion. Right, so n is something like this. It's like a disk, but I'm removing one point of the interior. That corresponds to the point that it is removed from the torus. So I have the inclusion here. And the proposition tells us that if we look at the induced map on degree 1 in cohomology, that map is 0. Okay, and I'm only focusing on degree 1. I'm not saying that J has to be 0. J is 0 only on degree 1. That's the claim. Okay, so we will use this fact to prove a few results. I'm going to skip the proof of this proposition now. So, as I told you yesterday, we need to compute the cohomology precisely of this manifold. I want to know the cohomology of that manifold, the punctured torus. So we will use basically what we have computed, the cohomology of the torus. So now I'm going to split the torus in a different way that we did it at the beginning of 2 circles. Now, U and V will be different. U is the punctured torus, and this is what I'm really interested in computing that cohomology. So I know the cohomology of the torus, and I want to compute the cohomology of the punctured torus. I'm going to take V, just a disk, about the point that it is removed. Oh, wait, so first, I forgot about this. Let's try to understand U. U, you have it here, is the torus minus a point. And I'm going to do a retraction. Like, remember how the puncture plane was retracted to the circle? What it was inside, we push it to the unit circle. Here, I'm doing the same. This point is removed. So I'm going to open it a little bit, and it will have the same homotopy type as this here. So this is T2. Okay. So that's U. Is that clear for everyone? So just think about the plane. If I remove a point, then I can do a retraction by stretching everything a little bit. And that's what I have here. So that is U. And now V is going to be a disk about the point that it is removed. So I'm taking here a disk. Right? Then what about U intersection V? It will be a cylinder, right? It's basically the disk minus an interior point. And we know the homotopy type of that. That is the circle. right? So this is something that I don't know the cohomology, but I know this cohomology, this one, and also this one. So we will use the Meyer vectoric sequence not to compute the cohomology of the ambient space, but of a smaller set, which is U. So let's put all of this together. Here, right? So V is here, is a point, that's why I have 0 and 0. U intersection V is the circle R and R. And this is what we know from our previous example. And what is here is exactly what we would like to compute. Again, because U is connected, I have R, right? Also here, we can simplify our exact sequence because UV is connected, so I can start from here. And that's the exact sequence that I have here. So this starts here. So this is the exact sequence of the Meyer vectoric sequence, and I'm missing this vector space and this other vector space. Okay, now here we need to use the proposition. Remember? This proposition goes from this cylinder inside the puncture torus here. That's the inclusion. And that map in cohomology in degree 1 is 0. So remember, U intersection V is the cylinder. U is the puncture torus. So this map is the one that we know that it is 0. Okay, so let's call this map alpha. The map alpha is exactly this map here. Oh, sorry, I didn't mean that alpha, that's wrong. I want this map, right? So sorry, that's not the alpha. I made a mistake there. It is this one here. Oh no, I did it right. Yes, sorry about that. Yes, this is alpha. Remember what is alpha? H1U, H1V, I have a one form omega U, a one form omega V, and I have to restrict. Okay? Now, in our example, this is 0. So alpha is a map, a form, and 0 here. And it is just restriction. Okay? And then using the proposition, we have that the linear map alpha is 0. Okay? So I'm using the proposition here to conclude that the linear map alpha has to be 0. Up to this point, any questions? Everything makes sense? Okay, so again, in the exact sequence, I don't have zeros. I don't have zeros. But now I have a map that is 0. Right? So the map alpha is 0. That means how do you compute now this? You see, you have this. Instead of putting R, what can I write there? I can put 0. Yeah, that's the map. And that is an exact sequence. That means that whatever this map is, this is an isomorphism, this map here. Right? Oh, sorry, I'm missing that too here. What else? From the same exact sequence. right? Because this map is the map 0. So this map, I can write it 0 goes to R. And that's an exact sequence. And I'm only missing one vector space in that exact sequence. So what is the dimension of H2?
Just 0.
Exactly. So this is trivial. Hence, the cohomology of the punctured torus is R on degree 0, right? Because it is connected. On degree 1, that what we computed here is R2. On degree 2, we computed that to be 0. And by dimension reasons, all of the other dimensions, it is trivial. So it's very similar to the torus, except in dimension 2 is trivial. Any questions here? So know that in this part, we use the proposition. The inclusion of the annular region into the punctured torus is 0. So this is like the previous proposition. And we will also use the same proposition later on. So that's important to note that we have used that. Right, so the other important aspect of this computation is, well, we can use the Mayer-Viettori sequence not only to compute the cohomology of the ambient manifold, but of some open set. Here we use U, but also it can be used to compute this, for instance. If we know the cohomology of the other spaces that are involved. Okay. Any questions on this computation? Yeah, we need, I don't know. Now we will go into the last problem of the class now. We will end the course on this example. So we're going to compute the cohomology of the surface of genus 2. In the same way that we will compute this, you can compute the cohomology of the surface of arbitrary genus. Okay? But I will do it only in this case. For the other one, you use induction, Mayer-Viettori sequence, and the same ideas that are involved here. Okay, so before we proceed, any questions so far? Okay, so let's move on. So now that's my manifold. So this is my manifold M, and I would like to compute the cohomology of that manifold. The surface of genus 2. And that's why we need the previous example, because we will not know, we need to know the cohomology of U. So I got it like this. And that's basically has the same homotopy type, has a torus minus a point. For V, the other part, and U and V have to be a cover of M. That means that the intersection is a cylinder. And we know that the homotopy type of the cylinder is the circle. So again, we know the cohomology of these three spaces, and that will help us to compute the cohomology of the ambient manifold M. Good. So let's see. So help me out to fill this.
So for the first line, that is R2 plus R2.
And it is important to write it that way because we will remember what comes from U and what comes from me. So, I mean, that's R4, but it is important to distinguish. And what about here?
That is R.
Here?
0. 0.
Right. Okay. So this is the major ellipsoid sequence. U intersection V is connected, so we can forget about the degree 0 and start in degree 1. And that's what I have written here. Okay? Because U comma V is, sorry, U intersection V is connected. Okay? Now, we would like to compute or to understand the map alpha. The map alpha that I have written there corresponds to this map. Okay? So again, this is just from the definition. That's what alpha is. I have a differential form, another differential form, restrict and subtract. Okay? But now, U intersection V is a puncture torus. Sorry, U. V is also a puncture torus. And U intersection V is the cylinder above the puncture. So by proposition, the map JU and JV are 0 in degree 1. Okay? And this is my proposition. So that means that the map alpha, that linear map, has to be 0. So again, what happens is that this exact sequence that has two vector spaces that I don't know, I can split it because this map is 0. Right? So I have 0, R, H2, and 0. So this map is a linear isomorphism, and H2 is equals to R. And also, because I have a 0 there, this map is also an isomorphism. That linear map is an isomorphism, and so H1 of M is R4. So that's it. So the cohomology of this because it is connected R4 and 0 otherwise. Right? So is this clear?
So generally, it only depends on the number of holes.
Right. So let's see. G is the genus. That's the same as the number of holes. So R 2 times G. For the torus, G is 1, and that's what we had, R2. For this one, we got R4 because we have genus 2. So the general answer, in degree 0 and on degree 2, they don't change, only on degree 1. Any other question? Great. So we have computed the dimension, the cohomology of many spaces in dimension 2. In higher dimensions, only the Euclidean space, because it turned out to be contractible, and the spheres. At the beginning, we saw that if two manifolds are diffeomorphic, then that map that it is a diffeomorphism induces a linear isomorphism in cohomology. So what you can extract from all of the computations is that all of these spaces are not diffeomorphic because they don't have the same cohomology. Okay? So that's something that you can get out of this, all of these computations. Also, we didn't look very much into some other aspect, but we have only computed these vector spaces for some manifolds. Something also that it is important to understand is an internal structure. That means the ring structure. Remember that differential forms can multiply by the wedge product, and the wedge product moves on into cohomology. So this is something that we didn't cover, but it is also something very interesting. So the ring structure here. In some cases, there is not much to say. For instance, for a sphere, the product is 0 because you only have cohomology on degree 0 and on degree n. And if you multiply those two, you will get something. I mean, there's nothing in between, so there's nothing interesting. However, for the torus, that ring structure is important, interesting. And also for the surface of genus G, you can take, because now you know that there are non-trivial elements in degree 1, and if you multiply two 1 forms, you will get a 2 form. So to understand the ring structure of this cohomology, you just have to know what happens on these products, multiplying 1 forms, or classes of 1 forms. So we are not going to go into that, but that's something that it is known and it is very nice. Any other questions or comments?
Yes, previously you used an argument where you said something about biconnectedness. We can conclude this.
About what?
Previously, when using the major vectorial sequence, go back. Can you go back? You used an argument that was along the lines of, oh, biconnectedness, we can conclude, and I didn't quite catch that. Can you go again to it, please?
Yes. So I used the argument of connectedness in several examples. Do you mean in this example or in which other example?
In this example.
Yes. Okay, let's see. So, so first, because we know that M is connected, I have R here. U is a puncture torus connected, V, and U intersection V is only one cylinder, so it is also connected. So we use connectedness to fill the bottom row. Now, in the next step that we use connectedness argument is this one here. This is connected. Not only do I put this R here, but when U intersection V is connected, the long exact sequence of the Mayer vectores simplifies. I can forget about this and I can start my sequence here. And that's what I wrote here. So here I use the fact that U intersection V is connected. So I can forget about the bottom row and start on degree 1. I don't know if you were referring to this. Moises?
Yes. Yes.
Okay. So, and this is something that we couldn't do for the torus because U intersection V were 2 cylinders. So there, that's why we had a longer sequence. Yeah, so here is where we use that part. I think that's the only case. Also here, maybe that's why I wrote this one here. Well, there was two reasons, but U intersection V is connected. So, and that's what I have here. I forgot the bottom row. But on the first one, no. So this is this one. And so on. So here, I really have to include the bottom row because U intersection V is not connected.
Okay, thanks.
Great. Any other questions?